Okay, thank you very much and welcome back again for this afternoon session. And this afternoon session we are going to see about ordinal logistic regression. In the morning session we have seen about multinomial logistic regression. And now we'll proceed to see about ordinal logistic regression. So as you remember in the previous sessions, there are occasions when the scale of multiple category outcome is not nominal in medical research, So if we do have an outcome variable more than two categories, at least three categories, and the categories are not nominal, rather if the categories are ordinal, so that the response variable is just ordinal response variable. So we will have such types of outcome variables, The outcome variable will be having three and more than three categories. And the categories are not nominal. They are rather do have an ordering nature, ordinal types of variables. So most medical and epidemiological studies will incorporate a number of ordinal types of response or outcome variables, Therefore, an ordinal response variable Y represents a level of standard measurement scale, such as, for example, the severity pain. We may just have a labeling like no pain, mild pain, moderate pain, and severe pain. So in this case, there is an ordering between the categories, So such types of categorical outcome variables with an ordinal or ordering nature will be modeled by using an ordinal logistic regression. And clinicians may specify an ordering of the severity of several component events with regard to the disease status of a patient, and may assign patients to the worst event, like for example, they are not at the worst level, none, or might be just the patient may have a heart attack, or other possibility is just the patient could have a disabling stroke, and the worst is the death. So having without any risk, that is no risk at all, having a heart attack or having a disabling stroke, and finally maybe death. So these types of variables could be also tell us an ordering nature, There is an increasing worsening condition of the patient. So there is an ordering pattern in the category of the response or the outcome variable. Another scenario, like for example, retinopathy status of diabetes mellitus patients could have three ordered categories. A DME patient without no retinopathy, one category. The second category, non-proliferative retinopathy. And the third category could be advanced retinopathy or blindness. So such types of ordering nature tell us there is an increasing severity or just a worsening condition of the patient status, So outcome variables could have such types of categories which are ordinal or ordering in their nature. And the predictor variables for this retinopathy status having three categories with ordinal nature could be a blood pressure and the duration of the DME patient, and other extra predictor variables could be considered, to just the patient to have no retinopathy or non-proliferative retinopathy, or maybe advanced retinopathy. So what factors could contribute for the patient to have either of these types of outcomes, which are ordinal in nature? So just I'm telling you or talking about the ordinary nature of an outcome variable could be there in medical research, So you can rank the values of the ordinary variables. We can rank. We can give a rank from the first to the last, from the smallest to the highest. We can give a rank or an order. But the real distance between the categories is not known because it is not numerically expressed, It is not quantitatively measured and numerically expressed. Therefore, we cannot know the distance between two ordinal categories. Simply what we know is there is an ordering or an increasing or decreasing rank between the categories. So that is an ordinal type of variable. And survey questionnaires, or maybe study participants who have been asked by using survey questionnaires, could choose answers from scales like strongly agree, disagree, or strongly disagree, no? So there are scales of measurement. So just giving a response from strongly agree to strongly disagree, there are a number of scales. So that scales could tell us there is an scaling or ordering between giving the response for the question. So such types of variables are ordinal. Even the nutritional status of a certain individual could be just categorized as nourished, moderately malnourished, and severely malnourished. So in this case, again, we are just talking about the ordinal types of outcome variables. So, ordinal logistic regression could be used to study the patient reaction to drug dosage again. You see? Another scenario or another example of ordinal types of outcome variable. Reaction for the drug dosage. So the reaction of patients for the drug dosage. So the possible reactions could be classified as no reaction, mild reaction, moderate reaction, and severe reaction for a specific drug dosage, you know. So such types of without any reaction, mild reaction, moderate or severe reaction are types of ordinal categorical variables. So the difference between the mild reaction and the moderate reaction is difficult to quantify or impossible to quantify. And it is only based on perception, you know. Mild reaction, moderate and severe reaction might not be expressed in number, but we can just have a perceptual understanding that the reaction is mild, moderate, or severe. So moreover, the difference between the mild reaction and the moderate reaction might be greater or less than the difference between the moderate and the severe reaction, you know. But we don't know it in number. So the difference between the mild and the moderate group with that of the difference between the moderate with the severe group might be less or greater, you know. But we don't know by how much it is higher or less than the other, because it cannot be expressed in number or it cannot be quantified. Rather, with perception, or we can have just an understanding that there is an increasing or decreasing order in the categories of the outcome variable. Therefore, ordinal regression is used with ordinal types of outcome variables or response variables, while the independent variables can be any type. They can be categorical or continuous. But the outcome variable in ordinal logistic regression is ordinal type of variable. So ordinal regression models are sometimes called cumulative logit models. That is the alternative name. We will see why they have been called cumulative logit model, you know. There is a reason to call this ordinal logistic regression as cumulative logit model. There is a reason behind that. Or because the ordinal logistic regression also typically uses the logit function, similar with the binary logistic regression and the multinomial logistic regression. Any logistic regression type uses the logit link function, because there is a logarithmic transformation of the outcome variable, as we have seen in the previous class. And also ordinal logistic regression with a logit link function is also called a proportional odds model. Proportional odds model. Again, here there is a reason behind calling this model as proportional odds model. We call it, therefore, ordinal logistic regression, cumulative logit model, or proportional odds model are alternative names for the same regression analysis method, you know. So some text could say cumulative logit model, other text could say proportional odds model, and in other textbooks you could get ordinal logistic regression. So these all are alternative names for the same regression method, you know. Okay, I will just tell you why this regression type is called as cumulative logit and proportional odds model, you know. Therefore, ordinal logistic regression aims to predict the probability of a case or an individual being at or below a particular level of a response variable in the category of the response variable, or being beyond particular level, which is the complementary direction from one or more predictor variables. Now, let me just tell you the difference between multinomial logistic regression and ordinal logistic regression here. Okay. Let's say, for example, we do have an outcome variable, the dependent variable. Okay. The dependent variable is having three categories, categorical variable, having three categories. Category 1, maybe okay. Category 1, category 2, and category 3. In multinomial logistic regression, what we are going to do is we compare the probability of being in category 2 against category 1, and we compare the probability of being in category 3 against category 1. That is in case of the multinomial logistic regression. But in the case of ordinal logistic regression, what we are going to do is the probability of being in category 1 versus the summation, the other two categories. Okay, so let me write it again. Category 1, category 2, and category 3. So I said the probability of being in category 1 versus or against the probability of being in category 2 and 3. So you see, C1 versus C2 plus C3. That is the comparison in the case of ordinal logistic regression. So this is a difference from multinomial logistic regression, you know. So we compare the probability of being in category 1 versus being in the category 2 and 3. Okay. Another possible comparison is the probability of being in category 1 and 2, C1 plus C2, the probability of being in category 1 and 2 versus the probability of being in category 3. That is it. You see how the comparison in the case of ordinal logistic regression differs from that of the multinomial logistic regression? That's the difference between the two. Okay. Again, if we do have four categories, for example, four categories for the dependent variable, that means C1, C2, C3, and C4, four categories. So what we are going to do is, you know, the probability of being, for example, if we want to compare the probability of being in category 4 against the probability of being in category 1, 2, and 3. So C4, the probability of being in category 4 will be compared against the probability of being in category 1 plus in category 2 plus in category 3. That is the probability of being in category 1, 2, and 3 versus the probability of being in category 4. Okay, the probability of being in category 3 and in category 4, C4, versus the probability of being in category C1 and in category C2. Okay, another comparison, the probability of being in category 3, in category 4, and in category 2 versus the probability of being in category 1. So these are the possible comparisons in ordinal logistic regression. So there are three possible comparisons if the outcome variable have four categories, you know. So this is the way how we are going to compare in the case of ordinal logistic regression. So the bullet which talks about is this one, what I have said here. So ordinal logistic regression aims to predict the probability of a case or an individual being at or below a particular level or category in the response variable or beyond. That means being in the group of 1 and 2 versus the probability of being in group 3 and 4, or the probability of being in group 3, 2, 3, 4 against the level 1 or the category 1. That is the multiple pairwise comparison will be made in ordinal logistic regression. So this is the basic idea in ordinal logistic regression, you know, which is different from the multinomial logistic regression. So binary logistic regression models the relationship between a set of predictors and the probability of a case being in a particular group, in a single group, you know, with respect to the dependent variable. But in the case of ordinal logistic regression, it is designed to model the cumulative probability of a case being or at below a given level on the orbital categorical variable. Yes? So in ordinal logistic regression, what we are going to do is the purpose or the aim of this ordinal logistic regression is to predict the probability of a case being at or below a particular level of the outcome variable, or beyond the particular category in that outcome variable, which is the complementary direction from one or more predictor variables, you know. So what I was telling you is that, for example, if we do have an outcome variable or a dependent variable having 4 categories, for example, category 1, category 2, category 3, and category 4. In the case of multinomial logistic regression, what we are going to do is we will make one of the categories as a reference, and we compare all the other categories against the reference. That is a multinomial approach. But in the case of ordinal logistic regression, what we are going to do is the probability of being in category 2, 3, and 4 versus being in category 1. So the probability of being in category 1 versus the probability of being in category 2, in category 3, and in category 4. So that will be the comparison. Okay, another comparison, the probability of being in category 1 and being in the category 2 versus the probability of being category 3 and category 4. Okay, the last comparison is the probability of being in category 1, 2, and 3 versus being in the category 4. So the probability of being in category 1, in category 2, and in category 3 versus the probability of being in category 4. So that is the way how ordinal logistic regression will be compared with that of the categories of the outcome variable, which is different from the comparison in the multinomial logistic regression. So this is the idea or the approach in ordinal logistic regression, you know. Okay, so binary logistic regression models the relationship between a set of predictors and the probability of a case or an individual being in a particular group, in a single group, you know, with respect to the predictor variable. The dependent variable. But ordinal logistic regression is designed to model the cumulative probability of a case being at or below a given level on the ordered category of the outcome variable. You see, that is why the name cumulative logit has been given for the ordinal logistic regression, because we are comparing the cumulative logit or probability of being in category 1 plus category 2 plus category 3 versus being in category 4. All the probabilities of these 3 categories are summed up or cumulated. So the probability of being, that is the cumulative probability, you know. So that is why cumulative logit has been given for ordinal logistic regression. So hereafter it will be clear for you. We are comparing the cumulative probability of a case being in category 1, 2, 3 versus the probability of being in category 4. Or the probability of being in category 1 and 2 versus the probability of being in category 3 and 4. We are summing or cumulative the probabilities of categories in the comparison. So that is why a cumulative odds model or the cumulative model has been given for ordinal logistic regression. So that is the difference of ordinal logistic regression from the binary logistic regression and from the multinomial logistic regression. Okay, so binary logistic regression uses the language of odds and logits, and therefore ordinal logistic regression uses the language of cumulative odds and cumulative logits, because we are comparing the cumulative log odds of a case being in category 1 and 2 versus in category 3 and 4. Or maybe the probability of the cumulative probability of being in category 1, 2, 3 versus the probability of being in category 4. That is why the cumulative logit or the cumulative odds is used in the case of ordinal logistic regression, because there is summation or accumulation of probabilities in between categories or the ordered categories of the outcome variable. That is why the cumulative odds or cumulative logit has been given for the ordinal logistic regression. So this is the reason behind why ordinal logistic regression is called as cumulative logit model. So therefore the formula for ordinal logistic regression will be in any type of logistic regression, since there is a natural logarithm transformation, always there will be ln transformation. The ln of the probability of the outcome variable y to be in less than or equal to j groups. For example, if we do have 4 categories again, C1, C2, C3, and C4, the probability of being in category J and less than J means the probability of being in category 3 and less than category 3. That means in category 1, 2, and 3. Versus the probability of greater than J, greater than 3. That is the category that is greater than 3 is category 4. So that is the formula. The probability of an observed outcome for a case, for an individual, being less than or equal to in group J over the probability of being that outcome variable greater than group J. So this is the way how the formula would be written. Is equal to, since this is a probability of an outcome variable y less than J over the probability of y greater than J is the odds, that is the success over the failure, P over 1 minus P. So this is replaced in the place of P over 1 minus P, you know. Since this is the odds, we can say the ln odds of the outcome variable y less than or equal to in group J is equal to the intercept AJ or alpha J plus beta 1 x1, the predictor variable x1 with its beta coefficient, plus up to the number of predictor variables that we have, bk, xk. That is the formula for ordinal logistic regression, you know. So where alpha j refers to the threshold or the cut point, which is analogous to the intercept. So, but the language here is not intercept in ordinal logistic regression. The language, instead of saying intercept, is it has been said cutoff point or threshold. Cut point in stata and threshold in SPSS. And in SAS it says intercept, you know. So saying threshold or cutoff point means simply the intercept. On the ordinary variable or ordinal variable outcome y star, making the transition from one category to the other category. And the beta k refers to the regression coefficient for the predictor variable x. So that is a general formula for ordinal logistic regression. So the natural log of the cumulative odds of a case falling into or at below J group the cumulative odds, the cumulative, why cumulative? I have said it previously. You need to just understand, you know. The probability of being in category 1, in category 2, and in category 3 versus the probability of being in category 4. So the probability of being in category 1, 2, and 3 are just cumulated, you know. So the log or the natural logarithm of the cumulative odds of a case falling at or below, falling at category 3 or below category 3. That means 3 to 1. That means the LAN odds of the outcome variable less than or equal to J group is referred to as the cumulative logit. This is said to be the cumulative logit because there is always the logarithmic transformation and the language logit has been used because there is logit transformation or logarithmic transformation. And why cumulative? Because we are just summing up the probability of being in 2 and more than 2 categories versus the other category, you know? So for ordinal categorical variables, the drawback of the multinomial regression model is that the ordering of the categories is ignored in multinomial logistic regression. If we plan to use a multinomial logistic regression for an ordinal type of categorical outcome variables, then the ordering of these categories will be ignored, you know. That is a drawback of multinomial regression for ordinal type of outcome variables. Okay. So, here again, another most important issue is that each logit formula or each logit of the ordinal logistic regression has its own intercept or threshold that is labeled as alpha j, but the same beta coefficient for a given predictor variable. That means the effect of independent variable is the same for different logit functions. What does it mean? Let me just explain it with an example, you know. Okay. Now, we are trying to just calculate the beta coefficient for a certain predictor variable x on the comparison of ordinal categories of an outcome variable C1 versus C2, sorry, C3. So now we are going to compare the probability of being in C1 versus the probability of being in C2 and in category 3. And again, we are going to compare the probability of being in category 1 and 2 versus the probability of being in category 3. Okay, if we do have a fourth category, for example, if we do have 4 category, let's add an one category over here, that is C4. C4. If we do have 4 categories of the outcome variable, just we are again going to compare another pair, you know, the probability of being in C1, in C2, and in C3 versus the probability of being in category 4. Okay, so the effect of this predictor variable x on the probability of being category 1 versus category 2 and 3 will be the same on the probability of being in category 2 and 1 versus 3. Sorry, this one is now in the case of this, since there is a fourth category, the probability of category 3 plus it will be the probability of category 4. Okay. So the beta coefficient of this predictor variable in each pairwise comparison will be the same. For example, if it is 0.4 here, then again it will be 0.4 here, the beta coefficient, and then it will be again 0.4. So the effect of this single predictor variable on each pairwise comparisons of the paired ordered outcome variable will be the same. So that is the proportional hazard assumption of the ordinal logistic regression. Meaning, the effect of each predictor variable on each of the pairwise comparison of the ordinal outcome variable is the same. So that if smoking is a predictor variable, the effect of smoking on a patient to have to be in the category 1 versus in category 2 and 3 is 0.4. And again, the effect of that smoking again for a patient to be in category 1 and 2 versus in category 3 and 4, again it will be 0.4 and so on. So it is a proportional hazard assumption. That means the effect of each predictor variable on each of the pairwise comparison of the ordinal categorical outcome variable should be the same, constant. That is a proportional hazard assumption. And that is why ordinal logistic regression is named again as the proportional odds model. This is the reason why ordinal logistic regression is also said to be proportional odds model. You see? So the reason why ordinal logistic regression model is called as proportional odds model is now clear. And the reason why ordinal logistic regression is called as cumulative logit model is now clear for you because of the reasons that has been explained now. Okay, so this is really very fundamental. So this is to mean that the effect of each independent variable is the same for different logit functions, for different pairwise comparisons of the orders of the ordinal outcome variable. So the effect of the predictors on the odds of, on the probability of falling into a higher versus a lower category on the dependent variable is the same across what? The categories, across the pairwise categories, as I have said, shown you with example. So that is an assumption that we need to check. Otherwise, if this assumption is not fulfilled, we will go back to the multinomial logistic regression. You know, if you remember in the morning session, multinomial logistic regression will be used in two conditions. One, if the categorical variable have three categories and if the categories are nominal. And two, if the assumption for ordinal logistic regression is violated. So that if the assumption of this proportional effect of predictor variables is violated for ordinal logistic regression, we will go back to the multinomial logistic regression. So we need to check this assumption. If the assumption is already fulfilled, then we go for ordinal logistic regression. But if the assumptions are not fulfilled, we will go back to the multinomial logistic regression. So that is the clear demarcation or difference between ordinal and multinomial logistic regression, you know, and which is very tough and very interesting. Okay, now let's continue. So ordinal logistic regression models cumulative probability, as I have said it, and now by now it is very clear for you why it is cumulative probability. Because we are comparing the cumulative probability of a case falling into categories or more than two categories against the remaining category. So it simultaneously estimates multiple equations because we do have multiple comparisons, you know. Category 1 versus the probability of category 2, 3, and 4. Okay, and one equation. The other equation is the probability of being in category 1 and 2 versus the probability of being in category 3 and 4. The second equation. Now the third equation is the probability of being in category 1, 2, 3 versus the probability of being in category 4. So three equations will be there for three pairwise comparisons for an ordinal variable, outcome variable, having four ordered categories. So these equations will be simultaneously estimated by using this ordinal logistic regression. And the number of pairwise comparisons will be the number of categories C minus 1. If you draw four categories, 4 minus 1, 3 pairwise comparisons will be there, similar with the multinomial logistic regression. So for our example, three equations will be estimated for the four category outcome variable. So equation 1 will be, for example, you do have category 1. If you do have 1, 2, 3, 4, 4 categories, category 1, the probability of being in category 1 will be compared with the probability of being in category 2, 3, and 4. One equation. The second equation is the probability of being in category 1 and 2 versus or compared to the probability of being in category 3 and 4. The second equation. The third equation is the probability of being in category 1, 2, and 3 versus the probability of being in category 4. There are three equations or three possible pairwise comparisons. So all of these, the three equations will be simultaneously estimated by using this ordinal logistic regression method, you know. So by now it is very much clear for you. And ordinal regression requires assuming that the effect of the independent variables is the same for each level of the dependent, you know, for the previous one. So if there is an x predictor variable, so the effect of that predictor variable or the beta coefficient will be here, for example, if it is 0.4 for this comparison group, again it will be 0.4 here. Again it will be 0.4 here. Because the effect of that predictor variable on each of the categories of the ordinal outcome variable is assumed to be the same. So that should be fulfilled. If that is not the case, then we'll just go back to the multinomial logistic regression. So I have said it repeatedly many times, you know, if we do have four categories, the probability of being in zero group, if it is coded as 0, 1, 2, and 3, the probability of being in zero category versus category 1, 2, 3. And then the probability of being in category 0 and 1 versus the probability of being in category 2 and 3. Okay, the third one, the probability of being in category 0, 1, and 2 versus the probability of being in category 3 will be compared, you know. So it assumes that each of these comparisons yield the same odds ratio or the same beta coefficient for a single predictor variable. So each of the predictor variables will have the same odds ratio or the same beta coefficient for each of these possible comparisons, you know. That is the assumption of proportional odds assumption. The effect of each predictor variable will be the same in each of these comparisons. The same odds ratio or the same beta coefficient will be there. So the name of the test that we are going to use to test this assumption is said to be the test of parallel line assumptions. The test of parallel line assumptions. Which tests this critical assumption which should not be taken for granted. Unless and otherwise you checked this assumption, there is no, you are not granted to go for doing ordinal logistic regression without checking this assumption, you know. Because as I have said before repeatedly, if the assumption is failed, then our result will be misleading. Okay. So, tables that are required in doing ordinal logistic regression in the result table or in the output of any software in doing ordinal logistic regression, these are very important outputs that we need. The one is the frequency of an outcome variable, because in order to see whether there is enough number of cases in each category of the outcome variable, we should see the frequency of the outcome variable. Plus again, we need to see the frequency of the all categorical independent variables. Again, in order to see whether we do have enough number of observation or frequencies within each category of the independent variables. And also we need to see the descriptives or the descriptive result for the continuous independent variables, the mean and the standard deviation. And we need to see the cross tabulation of the outcome variable versus each independent variable, you know. You should do the cross tabulation of the categorical outcome variable with the categorical independent variables in order to see and appreciate whether enough number of observations or frequencies are there. So in the output of any software in doing ordinal logistic regression, we'll have the case processing summary, the model fitting information, the parameter estimates table, the goodness of fit of statistics, and finally the test of parallel lines, which tests the assumption for proportional odds, you know. So these are required outputs of ordinal logistic regression. So now we'll have an example data set, you know. So consider the example data, which is a low birth weight study. The outcome variable is low birth weight and categorized with 4 categories. That means 0, which is greater than 3.5 kilogram or 3,500 gram. So that means it is a good birth weight for a baby. And the second category coded as 1 is in between 3 and 3.5 kilogram, or in gram it is in thousands. And the third category is coded as 2, which is in between 2.5 and 3 kilogram. And the fourth category is coded as 3. That is the very low birth weight, less than or equal to 2.5 kilogram. Okay, now we are just interested to see the probability of a newborn having a very low birth weight or being in the very low birth weight group versus the highest birth weight. The highest is not the coding, you know. You should see the birth weight, the record for the birth weight, 3.5 kilogram, above 3.5 kilogram, in between 3 and 3.5 kilogram, in between 2.5 and 3 kilogram. The highest is to mean that the highest birth weight level, not the coding, you know. So since if the birth weight of the weight of the newborn is less than 2.5, that is taken as the very low birth weight. So the probability of being in the very low birth weight against the highest, the remaining categories, being so that we are going to compare the probability of an infant to have a very birth low weight in this group versus the probability of having a baby with this category in summation. The probability of being above 3.5 plus the probability of being in the two ranges, 3 to 3.5, and the probability of being 2.5 to 3. So the probability of being in these three groups will be compared to the probability of being in this last group. Or we may compare the probability of being in these two groups, group 2 and 3, against the probability of being in group 0 and 1. Or we may compare the probability of being in group 0 against the probability of being in group 1, 2, and 3. That is the three possible pairwise comparison for this data set. And the predictors are a smoking status of the mother during pregnancy, which is categorical variable. Now we want to model the relationship between smoking status and very low birth weight or low birth weight. So smoking status as a predictor and low birth weight as an outcome variable, having 4 categories. So generally, in ordinal logistic regression, the event of interest is observing a particular score or less. That means the probability of being in group 1, 2, 3 versus 0. That means the probability of having a birth weight less than 3 kilogram. It means the probability of being in less than 3 kilogram means the probability of being in between 3 and 3.5 plus the probability of being in 0.2 and 3 and the probability of being less than 2.5. So that is being less, being at this specific group or beyond that, less than that group versus this group. Okay, so for the birth weight, we may model the following odds, you know. The odds, which is noted as theta 1, is the probability of a score of 3. That means a score of 3 means being in the third group. The probability of being in the third group versus the probability of being less than the third group. The probability of being the third group versus the probability of being less than the third group means being in the first group, in the second group, and in the 0 group. Okay. Theta 2, the second comparison, the probability of being in the third group or in the second group, the third and the second group versus the probability of being less than the second group. That means being in the first group, 1 and 0. The last comparison, the probability of being a score of in category 3, 2, or 1 versus the probability of being less than 1. That means the remaining category is category 0. having a birth weight of greater than 3.5 kilograms, that is less than 1. The category which is less than 1 is the category 0. So that will be the pairwise comparison for this given data set. The last category, which is coded as 0, doesn't have an odds associated with it, since the probability of scoring up to the last category is finally it will be 1. Because we are accumulating or adding up or summing the probability of each category till the last category. When we reach the last category, in summing the probabilities, the summation of each category till the last will be finally 100 or 1. So the last category will not have an odds ratio or a beta coefficient associated with it, because the summation of the probabilities up to the last category will be 1 or 100. So all of the odds are of the form, these odds, these comparisons will be just represented by this formula. Theta j, the probability of a score less than or equal to j, over the probability of a score greater than j, that is the odds, can be rewritten in such a way. The probability of a score less than j over the probability of 1 minus the probability of a score greater than j. That means p over 1 minus p. It means in place of p over 1 minus p, it is already replaced here. So since the probability of a score greater than j is 1 minus the probability of a score less than j, that is why it is written in such a way. So finally, the goodness of fit statistics. What does it tell us? If your model fits well, the observed and expected cell counts are similar. So the value of each statistic, that is a chi-square for this case, will be small and the p-value will be larger. The larger the p-value, the well-fitted the data or the statistics, because the null hypothesis says that the data or the model is well-fitted, and the alternative will say that the model is not well-fitted. So in order to accept the null hypothesis, which says the model is well-fitted, the p-value should be greater than 0.05. That is the case. So if the p-value is larger than 0.05, then we reject, if that is small, that means if the p-value is statistically significant, we reject the null hypothesis that the model fits if the p-value is small or less than 0.05. But if the p-value is greater than 0.05, then we accept the null hypothesis, and that means the model is well-fitted. So good models will have large observed significant levels or p-values greater than 0.05. So when we are looking at the output of any software in doing ordinal logistic regression, if we look at the goodness of its statistics, the p-value should be much greater than 0.05 to say the model is well fitted. So this is a procedure to do an ordinal logistic regression in SPSS, Okay, maybe you can use it when you got the material or the PowerPoint. So now let's come back to the example data set. So the birth weight coded as 0, 1, 2, and 3. 0 is greater than 3.5 kilogram, 1 is in between 3 and 3.5 kilogram, and 2 is in between 2.5 and 3 kilogram. And the fourth category coded as 3 is less than or equal to 2.5 kilogram. So hence our outcome variable has 4 categories, which are ordinal in nature, which are ordinal in nature. So we do have predictor variables like smoking during pregnancy, coded as 0 for no, 1 for yes. Premature labor history, again 0 for no, 1 for yes. And weight of the mother at the last menstrual period, which is a continuous predictor variable. So these 3 predictor variables will be used to predict the probability of a child to be in either of the possible pairwise comparisons of the ordering categories of the outcome variable. Okay, before trying to the ordinal logistic regression, there might be a probability or an opportunity to try some other regression methods. Like for example, if we try linear regression, this will be problematic because the assumptions of ordinary least square are violated when it is used with non-interval or categorical data. So if the outcome variable is categorical type of data, then the assumptions for linear regression will not be fulfilled. So linear regression could not be used for such type of data. If you plan to use ANOVA, you will have an option to use ANOVA if you change only the categorical outcome variable in the form of continuous variable, Unless and otherwise, you change the categorical type of outcome variable to the continuous type. By changing the categorical outcome variable into the continuous, it is possible to do with ANOVA. If we change the categories of the outcome into the categorical type of the outcome into the continuous. So this is not a bad thing to try, Okay, in the case of multinomial logistic regression, if you plan to use a multinomial logistic regression for this data, what will be the limitation is the ordering of the categories of the outcome variable will be lost. So using a multinomial logistic regression will be again inappropriate, So the appropriate one way will be just to use the ordinal logistic regression. So before we run our ordinal logistic regression, we will see if any cells are empty or extremely small in any of the categories of the predictor and the outcome variable by doing a cross-tabulation analysis with the descriptive statistics, So we should have such types of result. By doing this is a result obtained by doing descriptive statistics, So the categories of the birth weight categorical, which is outcome variable, 4 categories are here, and the frequencies are given here, with the percentage, the valid percentage, the cumulative percentage. So it seems that optimum number of frequencies are there. Smoking during pregnancy is categorical. Non-smokers and smokers, there are frequencies over here. So we can appreciate whether enough number of frequencies are there. The next one is premature labor history, which is categorical again. There are codes, yes and no, and the frequencies are given here. Just to appreciate whether there are enough number of frequencies within each category of the outcome and the predictor variables. And then for the continuous type of variable, that is the weight of the mother at the last menstrual period, whether there is a missing value or not, there is no missing value here, and the valid number of total cases or samples, 181. The mean and the standard deviation, and the minimum value and the maximum value. Okay, so by just having such descriptive statistics, we need to just have a look at on the inspection of the numbers of cases or frequencies within each category of the categorical predictor and outcome variable and that of the descriptive statistics for the continuous type of variable. By doing cross-tabulation, that means the outcome variable with the categorical ordinal outcome variable with the categorical type of predictor variables cross-tabulation, we need to just again see the number of frequencies within each cell. And again, birth outcome, the outcome variable with the premature labor history. Here it is 3, it seems somehow smaller number of frequencies, and otherwise it might be good, Okay, so here are the warning signs, regarding the above data, none of the cells is small or empty. There is no cell, 0 cell. So that is the message that is why descriptive statistics is needed. Okay, while running our model, because of the continuous variable, we will have the following warning message. We will see it while we are doing a space in a species, the software will consider the continuous variable weight of the mother as a categorical variable, but that was not categorical. So if the software considers the continuous variable as categorical, so there will be number of small cases or 0 cells. So it will tell us there are 0 cells in some of the variables it says. But we should not bother for that because the variable is continuous. Had it been categorical, we should be take care of that, But if the message is for continuous type of variable, that is not a problem. So technically there are empty cells because of continuous variable in our model, that is the weight of the mother. However, we are not worried about this warning message, because the warning message is because of the continuous variable. It is not because of the categorical variable. Okay, so we checked for empty cells when we did the cross tabulation with the respondent variable by each of, with the response variable by each of the categorical predictor variables. And then the table seems have an okay number of cases or appropriate enough number of cases. So here is the output of the SPSS software in doing this data set, The first one is the case processing summary with a warning message, which says there are this much cells with percentage. That is dependent variable labels by observed combination of predictor variable with zero frequency. So these zero frequencies are because of the continuous variable. That is the weight of the mother, which was not categorical. But the software considers the continuous variable. Each of the records of the continuous variable will be considered as a categorical by the software, So that's the problem. So we should not bother for that. Okay, so the case processing summary will tell us the outcome variable with its categories and the number of cases or frequencies with the percentage. And again, the categorical predictor variables with their percentage and number of observation or frequencies for each of the predictors. So the case processing summary will tell us the result about the categorical type of the predictor variables and the outcome variable. So here it is okay. So all of the samples, that is 189, has been used. So here is the case processing summary, which is the output of the SPSS for the given data set. We can see, or it has been already shown about the outcome variable, the categorical type of predictor variables, their categories, their frequencies, and the percentage. So that is the case processing summary that we need to look over here. So the case processing summary tells all the continuous and even the categorical variables are having enough number of frequencies, So the model fitness information table, we need to look over there. So which gives the minus to log likelihood for the intercept only model with that of the final model. So that means we are just testing the full model, that is the model with all the predictor variables. That is a final model compared with that of the intercept only model, the null model without any predictor variable. So by having a look at over here, the p-value is statistically significant. The null hypothesis says that there is no difference between the full model and the null model. So all the beta coefficients are 0 for the final model. And the alternative says that the final model is different from the intercept only model. So to reject the null hypothesis, the p-value should be much less than 0.05. And in order to accept the alternative one, to say that the predictor variables have a statistical significant association with the outcome variable. So really the final model is now statistically significant over that of the null model. So the model fitting information table will tell us whether the full model is statistically significantly different from the null model. The null model without any predictor variable. So this is the interpretation here in the slide. And the goodness of fit of the model, generally, whether the model is well fitted or not for our data, this is the goodness of fit table that we need to look over. So the null hypothesis states that the model is well fitted, and the alternative hypothesis will say that the model is not fitted. So in order to accept the null hypothesis, which says the model is well fitted, the p-value should be greater than 0.05. So in this case, both the Pearson and the deviance is greater than 0.05. And most of the time, we need to look over the deviance. So it is far greater than 0.05, so that we can say the model is well fitted. Model is well fitted. Okay. So this slide is interpreting about the result obtained over here, the goodness of fit test, in which I have said it already. And the last and the most important is the parameter estimate table. That means the individual effect of each predictor variable on the group membership of the categories or the ordinal categories of the outcome variable. So now let's have a look over here. The one which says the threshold in the spaces, and in stata it will say cut points. These are the intercepts, the intercepts. So we are not interested to interpret, but just what does that mean? To clarify what does it mean for you is, I will say something on that. But we are not interested to interpret the result of intercepts in writing any research work, But the meaning of these thresholds or intercepts should be understood by you. So the first threshold, which says birth weight cut 0, is the probability of being in category 0 versus the probability of being in category 1, 2, and 3. The first one is talking about that. And the second one is the probability of being in category 0 and 1 versus the probability of being in category 3 and 4. The probability of being in 2 and 3. And the last and the third one is telling about the probability of being in category 0, 1, and 2 versus the probability of being in category 3. Remember the coding for the outcome variable categories. The codes were 0, 1, 2, and 3. So the last category that is coded as 3 will not have any beta coefficient associated with it, because the summation of all the probabilities up to the last category will be finally 1 or 100. That is why the beta coefficient for the last category is omitted here. And it has been said before, So this is the way that how we interpret. Even though we are not interested to write the interpretation for the intercept, So the one which says the location is the most important thing that we are going to interpret. That means this is the weight of the mother at the last menstrual period with a beta coefficient of negative 0.011. And the p-value is statistically significant. Okay, now compared to those smokers, that is 1 as a reference, those who are not smokers, 0, again, it does have a negative beta coefficient. Being a non-smoker will decrease the probability of getting a very low birth weight baby, that means. And the p-value is statistically significant. And again, for premature labor, compared to those who were having a premature labor, those without a premature labor are less likely to get a very low birth weight. That means because the beta coefficient is negative. And the p-value is statistically significant. And actually, we need the odds ratio in the form of e raised to b. E raised to beta should be reported, That is what we want to use for the interpretation of the data. But by default, in ordinal logistic regression pathway, we may not get the way to report the odds ratio. I will just tell you the other way in order to get this odds ratio. Okay, so this is a parameter estimate table which shows whether each individual predictor variables have a statistically significant association with the group membership of the outcome variable. So all the 3 variables have a statistical significance relation or association with the group membership of the outcome variable, So if we run this similar dataset with Stata software, the same result will be obtained. The birth weight is negative coefficient. Smokers, now the reference category has been changed for this Stata, because we can choose a reference group in Stata. So compared to non-smokers, smokers are now the comparison group. So the beta coefficient is positive here. In species, compared to smokers, non-smokers are compared, But in this case, non-smokers are compared with smokers. So the beta coefficient will be positive. And history of premature labor, here in this case again, no history of premature labor is a reference, and history of premature labor is a comparison group. So that will be why the beta coefficient is positive here. Because in Stata, we can choose either of the categories to be as a reference. But in SPSS, what does it do is the category of the predictor variable with the highest frequency will be the reference group by default. So we cannot change that. And there is a way to change that reference somehow if the predictor variable is having only binary responses, you know. So in anyhow, we can appreciate that the three predictor variables are statistically significantly associated with the group membership of the ordinal categorical type of outcome variable, or that means the low birth weight. Okay, so the previous table contains the estimated coefficients or beta coefficients for the model. The estimates labeled as cut in Stata and threshold in SPSS are the intercepts. Look over here, you know, what I forget to show you is that the cut 1, cut 2, cut 3 in Stata, these are the intercepts. So the interpretation is similar what I have said previously. For example, the cut 1 is interpreted in such a way. The probability of being in category 0 versus the probability of being in category 1, 2, and 3. And the cut 2 is the probability of being in category 0 and 1 versus the probability of being in category 2 and 3. And the last one, cut 3, is the probability of being in category 0, 1, and 2 versus category 3. For the last one, for category 3, there will not be any beta coefficient because the probability of the cumulative up to the last category will be finally 100. Okay. So those which are labeled as cut in Stata and threshold in SPSS are the intercepts for ordinal logistic regression. Okay, but we are not interested to interpret this one, you know, but just for the interest of understanding, I have just interpreted such things for you now. So for example, for now there are also the coefficient for these predictor variables, and the coefficient for premature labor history, which is coded as 1 yes and 0 for no, independent variable in Stata is 1.076, which is over here, 1.076. So women with a premature labor history are 1.76 times more likely to give a low birth weight baby compared to the normal birth weight baby. The word normal birth weight baby refers to the summation of the three categories: the 0 category, the 2 category, and the first and the second category. Okay, so now in the parameter estimate table, we see the coefficients with their standard errors, the z statistic, the p-value, and the confidence interval. And smoking, premature labor history, and weight of the mother are significantly associated with the outcome variable. So the estimates in the output are given in units of ordered logit or ordered log odds. So therefore, for weight, we would say that for a 1 unit increase in the weight of the mother, we expect, since it is the beta coefficient is 0.01 negative, a unit increase in the weight of the mother, we expect a 0.01 decrease in the log odds of low birth weight, given all other predictor variables are held constant. That means we have controlled the effect of all other predictor variables. Why we say a decrease in the log odds of low birth weight? Because the beta coefficient for this weight is negative 0.01. So this is a mathematical interpretation for the result obtained over here. Okay, for smoking status again, we would say that for a 1 unit increase in smoking, it is to mean that going from non-smoker to smoker, because it is a categorical variable, we expect 0.612 increase. It is a positive beta coefficient. in the log odds of the low birth weight, given all other predictor variables are held constant. That means all the predictor variables have been entered in the model and the confounding effect has been controlled. So the thresholds are not used in interpretation of the result, as I have said before. Thresholds in the stata, cut points in thresholds in spaces, cut points in stata, and SAS will say intercepts. Okay. So now this table is just shows us the result not only in the form of beta quotient but also in the form of odds ratio. So hereafter we will interpret the result in the form of odds ratio or in epidemiological language, you know. So the thresholds are interpreted in the same way as I have said before. Okay. Smoking compared to non-smokers, the effect of smoking during pregnancy on getting the low birth weight baby is now positive, you know, positive 0.612. And the odds ratio or E raised to B is 1.8. Okay. And again, premature labor history with compared to with those mothers without history of premature labor, those with premature labor history are again positive coefficient and with odds ratio of 0.9 times more likely. Okay, weight of the mother at the last menstrual period is negative beta coefficient, so the odds ratio will be less than 1 because the beta coefficient is negative here. If the beta coefficient is positive, the odds ratio will be above 1. If the beta coefficient is negative, then the odds ratio will be below 1. So it is 0.989. That means with a unit increase in the weight of the mother at the last menstrual period, so the probability of getting a low birth weight baby will decrease by 0.989. That means. So now let's continue with the interpretation of this result. Okay, this result could be also obtained by using a stata software in order to just report the odds ratio in the form of odds ratio, you know. So similar, for the weight 0.989, for smokers 1.8 times, for premature labor history 2.9 times. And the thresholds are again labeled as cut point here. So now we are on the verge of winding up the theoretical session of this ordinary logistic regression, you know. So in the parameter estimates table result, what we did is written here in the PowerPoint, you know. So assuming categories on the dependent variable are ordered in ascending fashion, moving from the lower to the higher values. Ascending is moving from the lower to the higher in spaces, you know. So the default, which is in spaces, by default spaces will just select the ascending order from the lowest to the highest. That means the code given 0 will be the reference. So 0, 1, 2, 3. So compared to 0, by the way, is greater than having a birth weight of greater than 3.5 kilogram. So that will be compared to in being category 0, the probability of being in category 1, 2, and 3 will be compared by default. But we can change that reference category, you know. So we can interpret an estimated regression slope as the predicted change in the log odds of a case falling above a given category J on the dependent variable, holding the remaining predictor variables are held constant. That means being the confounding effect of predictor variables has been controlled. So this parameterization allows the signs of the regression coefficients to be interpreted as in the standard linear regression. If positive beta coefficient, there is an increasing risk. If negative beta coefficient, a decreasing likelihood of being in that category, you know. The thresholds just already have said it. Okay. So in the column which says odds ratio, we see the results presented as the proportional odds ratio. We say proportional because the odds ratios of a single predictor variable are the same across different categories of the outcome variable. That is the word proportional. So there will be the same proportional odds ratio for a single predictor variable across different categories of the outcome variable with the confidence interval. So we would interpret the proportional odds ratio pretty much the same as the binary logistic regression, you know. The interpretation is similar with the binary logistic regression. Like for example, smoking having a p-value of 0.028 and premature labor, p-value of 0.007 are positively and significantly associated with the low birth weight. The low birth weight coded as 3, below 2.5 kilogram, versus the remaining categories. That means 0, 1, and 2. Okay, so we might, the weight of the mother at last menstrual period is negatively and significantly associated with the low birth weight. The p-value is less than 0.05, but the beta coefficient is negative. So there is a statistically negative association or relation with the outcome variable. So the way the mathematical or the statistical interpretation for these variables will be as follows, you know. For weight of a mother, we would say for a 1 unit increase in the weight of the mother, the odds of low birth weight versus the combined middle and higher categories. You remember these categories. The odds of low birth weight, that means the odds of being in category 3 versus the combined odds, that means the probability of being in category 2, 1, and 3. The combined middle and higher categories are 0.989 times less likely, given all other predictor variables are held constant. Since the odds ratio for weight of the mother is 0.989, which is less than 1, so the probability of being in the low birth weight group versus the probability of being in the middle and the higher groups is 0.989 times less, with a unit increase in the weight of the mother, you know. If the weight of the mother increases by 10 kilogram or by 10 pound, because it is measured in pound, and the formula for the odds ratio is e raised to beta, that means e raised to, sorry, before saying beta, because there is exposure variable here, is the power of the intercept a plus beta 1 x1. You see? Or maybe let's just leave the intercept because we are interested for the interpretation of the beta coefficient for the predictor variable. So e is the power of beta 1 x1, you know, the beta coefficient for the predictor variable x. So the beta coefficient for the weight of the mother is negative 0.011438 from the table, the beta coefficient. And the predictor variable x is now the weight of the mother. If it increases by 10, we will multiply this negative 0.011438 by 10. And the power of this multiplication will be finally 0.892, the odds ratio, with a 10 pound increase in the weight of the mother. Okay, so it will be less likely by 0.892 times. If we are interested to see the percentage, the reduction of the percentage, we should subtract this number from 1. 1 minus 0.892. Then finally it will be 11.2%. So it implies that there is an 11.2 percentage reduction in the odds for the low weight baby per a 10 pound increase in the weight of the mother. You see? Okay. One feature of the proportional odds model is identical to the binary logistic model, is that we can reverse the direction of the model by simply changing the signs of the coefficient. That means now in this case we are comparing the very low birth weight baby against the remaining categories. Now, if we reverse the comparison, that means if we are interested to know the probability of being in the highest category of the birth weight, that means in the zero code, that means greater than 3.5 kilogram. If we are interested to compare the probability of this category, the previous one was the probability of being in category of less than 2.5 kilogram. In that case, it was negative beta coefficient, you know. But if we reverse the comparison group, that is, if we are interested to know the probability of being greater than 3.5 kilogram, that means in category 0, then the beta coefficient, which was negative here, is now will be made as positive. That is it. If we reverse the comparison, the comparator category, then the beta coefficient will be negative for the previous one and now for positive for this one. So if we are interested in modeling the heavier birth weight, that means greater than 3.5, coded as 0, versus the lighter weight baby, that means the lighter weight baby means being in the category of 1, 2, 3. Yes. So being the probability of 0 versus being in the probability of the remaining 3 categories, 1 plus 2 plus 3. This is the heaviest baby having 3.5 and above, and these are the lighter weights between 3 and 3.5, between 2.5 and 3, and below 2.5. That is it. Now we are reversing the comparison now. So the beta coefficient will be positive here because the category is now reversed. So the 10 pound increase, okay, with a unit increase, with a 1 pound increase, will be is the power of beta. So the odds ratio is 1.0115. So if we are interested in modeling heavier versus lighter babies, then the estimate of the odds ratio for a 10 pound increase will be is the power of the beta coefficient, this one multiplied by 10, will be the odds ratio is 1.12. So in terms of percentage, 1.12 minus 1, it will be 12% increase, you know. So this estimate indicates that there is a 12% increase in the odds of a heavier baby with a 10 pound increase in the weight of the mother. That means if the weight of the mother increases by 10 pounds, so that's the probability of getting the heavier baby or birth weight baby will be increased by 12%. Okay. Now let's proceed with the remaining variables, you know. Women who smoke during pregnancy tend to have lower weight babies. This, the association is negative, you know. Women with a smoking history during pregnancy tend to have lower weight babies. So the beta coefficient will be positive because smoking will make a mother to have a more probability of getting a lower weight baby. Okay, so the estimate of the odds ratio for a lower versus heavier baby, the word heavier refers to the lower is the category 3. That means the probability of being category 3 versus the probability of being in category 2, 1, and 0. That is it. Is the odds ratio is 1.84. So women who smoke during pregnancy have 1.84 times the odds of lower weight baby versus heavier baby or heavier weight baby than women who do not smoke. That is the interpretation. And similar to the discussion for weight of the mother, the estimate of the odds ratio for a heavier versus a lighter baby will be reversed, you know. So the beta coefficient, which was positive previously, will be negative now. So the odds ratio will be below 1 in this case. So this estimate indicates that the odds of a heavier baby versus a lighter baby is 46% less likely. You see, if a mother smokes during pregnancy, the probability of getting a heavier baby compared to a lower baby will be reduced by 46%. If she smokes, the probability of getting a heavier baby will be less likely. That is the interpretation. How this 46 is obtained? You subtract 0.54 odds ratio from 1. So that is a percentage of the decrease in the probability of getting a heavier weight baby, you know. So women with premature labor history again tend to have a lower weight baby versus the heavier weight baby with a negative beta coefficient, you know. So women with premature labor history tend to have lower weight births. Therefore, the association is negative. So the estimate of the odds ratio for a lower versus a heavier weight baby is 2.93. So, and actually the association is not negative, it should be positive over here, because a premature labor history increases the probability of getting a lower weight births. So the association is positive, not negative, sorry. And that is why, since the beta coefficient is positive, then the odds ratio will be above 1. So the probability of getting a lower weight baby will be higher. So the odds ratio is 2.93. So women with premature labor history have 2.93 times the odds or the probability of having a lower weight baby versus a heavier weight baby. The word heavier refers to, and the word lower weight baby refers to the categories that are coded in the outcome in the data set. That means the probability of having a lower weight baby in the category 3, that means below 2.5 kilogram, versus the probability of getting a heavier weight baby, that means in category 0, which is greater than 3.5 kilogram, and the probability of being in category 1, which is a birth weight between 2.3 kilogram and 3.5, and again the probability of being in category 2, that is weight between 2.5 and 3 kilogram. That refers to, you know. So the probability of getting a lower weight baby will increase by 2.93 times, being in the heavier groups of birth weights, compared with women without the premature labor history, you know. So similar to the discussion for the weight of the mother, again, if we reverse the comparison of the groups, the estimate of the odds ratio for a heavier versus lighter. Previously we were comparing the lighter or the lower birth weight baby versus the heavier. If we reverse this comparison, that means if we compare the heavier birth weight versus the lighter or the lower birth weight, then the beta coefficient will become negative now. Previously it was positive. It should be positive over here, you know. So now it will be negative. So if we make it in the form of e to the power of beta, the odds ratio will be below 1. So this estimate indicates that the odds of getting a heavier birth weight baby versus the lighter weight baby reduces by 0.34 times, or 66% less for a woman with premature history. This 66% is obtained by subtracting this 0.34 from 1. So that the probability of getting a heavier baby, that means being in category 0 above 3.5 kilogram, versus the lighter, that means being in the category 2, 1 and 3, is decreased by 66% compared with women without, with premature history of labor, you know. So that is the issue of the interpretation for the effect of predictor variables on the group membership in the ordinal categories of an ordinal logistic regression categorical variable, you know. Okay, the last thing that we are going to check is the assumption for ordinal logistic regression. And we have said that the effect of each predictor variable on across categories of the outcome variable are the same beta coefficient or the same odds ratio. And that is checked by using the test of parallel lines. The test of parallel lines that is said to be the parallel regression assumption. Parallel regression assumption. So, for example, if we do have two possible comparisons, and if we express this comparison in the form of logistic regression, like in terms of binary logistic regression, the first logistic regression will be models the odds of the probability of an outcome variable y being in category 3 versus the probability of being in category 1 and in category 2, the first comparison. The second comparison is the probability of the outcome variable y to be in group 2 and to be in group 3 versus the probability of the outcome variable y in group 1. So the effect of a predictor variable for all these two combinations of pairwise comparisons should be the same. That is the beta coefficient or the odds ratio should be the same. So test of parallel lines is a test of whether the regression coefficients would be the same or different across these two regression models. So in other words, the effect of the predictors are the same across levels of the dependent variable. That is assumption that should be checked, you know. And we need to test this proportional odds assumption. If the p-value is greater than 0.05, the assumption is already fulfilled. If the assumption is less than 0.05, the assumption is already violated. So that is a test of parallel lines that we need to check. For this example data says the test of parallel lines indicates that the p-value is 0.614, which is much greater than 0.05, and that indicates the test of parallel lines or the proportional odds assumption is fulfilled for this data set. So we can proceed for the interpretation of our results. Okay, so this is all about ordinal logistic regression, conceptual and theoretical idea, you know.